Research mathematics, as I think is well known, has two extremes between the problem solving and theory building. So the problem solvers, they think about things like, as we did in R.Diestel's theorem in the introductory chapter. So the question there was, can we find a k-connected subgraph in a graph if the average degree is large enough? That's a natural question, and the answer is yes or no, where large enough means some function of k. And that's a concrete problem, it's an interesting problem, and one doesn't obviously see the answer, so off we go. And one can take that to extremes and ask, well, what function exactly is fast-growing enough to ensure that? And we also got an answer to that as sort of roughly 4k. And this is taken to extremes in something called extreme graph theory, which we'll get to later in the course, which is an important part of graph theory, not one that I specialize in, but it's an important part, but at least about half of graph theory, where particular values of invariance that are needed or ensure some other things are studied and targeted as concrete problems. And in extreme graph theory, it's very easy to pose exact problems. Does this or that growth rate of a function suffice to ensure something else? And they're also often very difficult to answer. And if they're not difficult enough to answer, you can always ask more precisely, well, what exact growth rate is it that you need? And there's an infinity of unsolved questions there, very, very concrete problems. At the other extreme, there's theory building. So what do those people do in mathematics? Well, sort of the problem solvers would say, well, they just make up problems that nobody ever asked about out of thin air, and they concoct some definitions, and then they make notions that nobody ever cared about, and then they prove how these notions hang together. Yes, that's what we do. And the responsibility in doing that is enormous. Anybody can think of definitions and then ask stupid questions about how these definitions are related, these notions are related. So there's a lot of responsibility in getting it right. But if it is well done, it leads to some beautiful mathematics. And interestingly, good theories tend to become applicable at some point. Not always, but often. So the two are interconnected. And of course, it's equally possible to ask obvious questions in the problem-solving scenario that lead to utterly useless mathematics. So problem solving isn't always by definition good. It can lead you to case studies that just go on and on and on and on and on, and that you have no insight, you have no sort of more general structure that you can use elsewhere or that somehow explain things. So what is good mathematics and what is bad mathematics is a notoriously difficult question, but it's a question we must ask ourselves. So it's easy to, and a temptation to just say, well, I'll think about this because lots of famous people have done that too and haven't been able to solve it, so there must be a good problem. Well, often it is, but let's check every time we do it. Okay, so what we do today is somewhere in the middle between those two. We're targeting concrete questions, but the questions arise from some background that we've established before, and the background now is connectivity. And so first, let's look at two connected graphs, and ask, what do they look like? That's a typical question in the middle ground. We have some structures that our sort of general theory throws up, and then we say, well, what do these things actually look like It's not a concrete question like what is the best function, blah, 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 but it's still, you can't cheat so much. I mean, you can prove things that are useless, but okay, let's see. So what do two connected graphs look like? Okay, so the first proposition, 311, says that the three connected graphs are precisely those, the two connected graphs are precisely those that you can construct as follows. You begin with any cycle, and then when you've constructed some two connected graph, you, let's call it H, you add an H path. So that's a path that joins two vertices of H and otherwise lies entirely outside. It might be a single edge that wasn't an edge of H, or it might have more vertices, and then you keep doing that. And so on. And it's sort of easy to see that all graphs that you can construct in this way are two connected, cycles are two connected, and whenever you add a path like that, you remain two connected. So the interesting thing, if any, is the converse. Can we construct every two connected graph in this way? So let's give ourselves an arbitrary two connected graph, G, two connected. Let's try and construct it in this way. Okay, first, to get started, we need a cycle. Does every two connected graph contain a cycle? Yes, obviously. Why? Why exactly? Yeah? Yes, very good. Yeah, but that's a heavy gun, big gun. So let's start with the observation that vertices have mean degree at least 2, otherwise the graph can be two connected. And then we know that this vertex doesn't separate its neighbors. That's the definition of two connected. All right, so there's a path. And there's our cycle. So we have a cycle. Okay, very good. And then we just say, okay, let's consider a maximal graph constructible in the prescribed way. And I claim that this is the entire graph G. Okay? And here's a false proof for that. Suppose it isn't the entire graph G. Well, if there's a little v that we haven't covered, then let's find a path, take any path to what we have covered. Let's look at the last edge. Let's call that vertex U before we hit. And then we know that the hitting vertex doesn't separate U from the rest of what we've covered. So there's a path from little u to the rest that avoids this, and there's our additional H path that contradicts the maximality of this. End of proof. Looks good, eh? I told you it's a false proof. Maybe that was false. Or maybe not. It's only a small mistake. But the sort of mistake that I make all the time, and you probably too, or maybe not, but I do. So that's why I keep throwing these mistakes at you, because they're so easy to overlook. Where was the error? It's not clear, is it? Well, I said, suppose we haven't got G at the end. let's look at a vertex that we haven't covered. There's the mistake. Can you see it now? Is it possible? Yes?
Is it that we don't know that additional vertex even exists?
Correct. We don't know whether such a vertex exists. That's what I claim now, being sober again. So it is possible that we have covered all the vertices, and yet we're not equal to G. How can that be? Only if there's an edge missing, or several edges missing. Yes. That can actually happen in principle, but such an additional edge would be another H path too. Which is why I keep insisting on that possibility when I talk about what they are, what H paths are. Right, so there's indeed a contradiction now. We don't need a V. If we're not maximal, there exists an additional H path. End of proof. Yeah, question?
No, it's just the definition of covering, because does covering mean covering all the vertices and edges?
Yeah, that's what my informal usage of the word covering. Yeah. Mm-hmm. Okay, so that's what the two connected graphs all look like. That's not a deep theorem, but it is sometimes useful. So next question, if our graph is not two connected, but just connected, can we take an outside look and see the two connected graphs making it up somehow? And if so, can we say anything about how they are interrelated, something like that? So can we find something like building blocks of any connected graph that are something like its two connected subgraphs, so that we can build the entire graph out of these blocks. Like you can build any graph, not a connected graph, any graph out of its connected building blocks, namely its components. And you can say something about the internal structure of these, or the external structure between these components, and what you can say about them is that such a structure doesn't exist. Right? They're just a set of components. There's nothing more you can say about the components than they're distinct. Right, but maybe we can say something more about these building blocks. Now, are the two connected subgraphs good candidates for building blocks of any connected graph now? Well, no, not really. Here's a two connected subgraph, here's another one, and here's another one, and here's another one. Right, so these intersect awfully. So let's go for the maximal ones, right? That's better. So a maximal two connected H and G looks like this, right? And then, if that's a maximal one, if that's not the entire graph G, if it is, fine. If not, they're not going to be additional edges, because then it wouldn't be maximal. We can just add them. But there might be additional vertices, so there might be another vertex here. And how can this hang on here? Well, only like this. If we take a maximal two connected subgraph containing this one, suppose it exists. It might be it might not exist. Then this building block can hit this building block only in one vertex, because if they met in two vertices, then the whole thing would be two connected, contradicting both maximalities. So we might get something like this. Right? Okay. That looks good. So we might be tempted to take this line here, maximal two-connected subgraph of G, as our definition of blocks. Until someday we discover a graph that looks like this. That's connected, and it doesn't decompose into its blocks because there's this nasty little edge there. Okay, then we would say or and bridges. A bridge is an edge in a graph that disconnects its ends in a connected graph. Yeah? Is that good enough? Okay, here comes this nasty question again. We don't know. Right? For all we knew, this was good enough. Until someday we discovered such a graph. I thought, oh yeah, I could have thought of that. But we didn't think of it. Same as with the false proof earlier. Now we're defining things. It's still a serious activity. We're looking for a good definition of block. And that looked like a good definition until we saw that. And now we're saying, oh yeah, okay, we're making amends. We're changing that. But what enables us to say, well, this is a good definition now? Wait a few more days and find something else? The answer is we don't know. But we have a strategy for dealing with such things, and that is sort of, that was invented by, who do you think invented this strategy? Well, you don't know it yet. Socrates. Socrates, Greek philosopher. He was in a more serious situation when he had been convicted of seducing the young people of Athens with his revolutionary ideas and questioned the authorities and the establishment and so on. So he was convicted and he was in jail and he was sentenced to death. Then his disciples came along and said, well, look, master, we've prepared everything. You can run away. You can escape and it's all done. And then Socrates said, wait a minute, no, this is not how it works. We have our laws, and laws mean that we must either abide by the laws or we must change them. We didn't get round to changing this bad law, of which I'm guilty of having contravened, and so I'm afraid it is just that I shall be poisoned. And he drank the poisoned chalice and died. So that's how Plato relates the story. And what can we learn from it? That is how we deal not with laws, well, maybe true, but with definitions in mathematics too. We work with the current definition as long as we can't think of a better one. And when we get to a point where we can think of a better definition, then we can say, okay, either we stick with the original definition and then just say it doesn't apply to all graphs that we want it to apply to, or we change the definition. But we must always work with some definition and make our minds up what this definition is. What we don't do is say, oh, well, I think blocks are more like this, and on a Tuesday you say, well, no, blocks should also include that, on a Wednesday, something else, right? Academic disciplines where this is how they work do exist. Mathematics is not one of them. Okay, so end of philosophy for now. So the definition could be that. What we really use is maximal connected cut vertex free subgraph. That's the definition of block. Now, I replaced to connected with cut vertex free because it also covers bridges. But this is, I mean, this is a big gamble. Right? This is just something I'm making up now, hoping that what we want to capture is always covered and it doesn't cover anything we don't want to capture. But that's our working definition now, and it has worked for the last 20 years, so chances are not too bad. Okay, that's the definition of a block, a maximal connected cut vertex free subgraph where the cut vertex free refers to that subgraph. So this first maximal two-connected graph, of course, contains cut vertices of G, this one here and this one here. But it doesn't have its own cut vertices because it's two-connected. Okay. Right. And so let's look at some properties of blocks now by that definition. I'm not going to write them up, but let's just mention them. First property is that different blocks share at most one vertex. Right? If they had another vertex in common, so this one as well, then the whole thing would be cut vertex free. If this is cut vertex free and that is cut vertex free, something that needs checking. So they share at most one vertex, and any vertex that they do share that lies in two blocks is a cut vertex of G. Why? Because it separates in G vertices of the two blocks, other vertices. Right? So this wouldn't be a block all by itself if it's contained in that one. So you can have an isolated vertex. Next discovery. An isolated vertex here is a maximal connected cut vertex free subgraph. Ooh, do we want it? Yes. But it's one of those moments where you begin to doubt the definition that you just proudly came up with 10 minutes earlier. Yeah, but yeah, let's say we want it. Anyway, we're mostly concerned with decomposing connected graphs here, so it doesn't really arise. Okay, so every vertex that does lie in different blocks is a cut vertex of G, and it separates. So cut vertex means it's a separating vertex. It separates two other vertices that are in the same component, that are not normally separated. Okay. Next question, every edge lies in some block. Oh, that nearly went wrong up there. Now this edge does lie in a block because it is a block with its ends. Can you prove that? Every edge lies in some block. Mm-hmm.
And edges connected with some vertices, so if it's not inside the block,
Sorry, yes, carry on.
that block wouldn't be maximally connected.
Yeah. So let's take it from the definition. So an edge itself, with its ends, is a cut-vertex-free subgraph. And just make it maximal, and then it's contained in that. Right, sort of same autopilot proof that we had a few days earlier. Yeah, so every edge lies in a block, and G is the union of all its blocks. Right? Every edge of G lies in a block, so every vertex incident with an edge obviously lies in a block, and every isolated vertex is a block. So every graph is the union of its blocks. Okay, so what about structure? Can we say anything about the structure of how these blocks are related to each other? Well, we don't have, I mean, this looks like a tree, doesn't it? Sort of from very far away. We can't have blocks sort of doing that, because then the union of those blocks involved in such a cyclic arrangement would itself be cut-vertex free if its ingredients are, and that would contradict their maximalities. So the arrangement of these blocks is tree-like. They don't form a cycle of blocks. Okay, we'd like to formalize that. So we'd like to come up with a definition of a concrete tree that formalizes this intuitive picture that the blocks have a tree-like structure. Okay, where's the tree? Definition. What are the vertices of that tree? Well, obviously the blocks, huh? And when, so let's talk about a connected graph. Otherwise, every component would be such a tree. And what is, when do two of these form an edge? Well, if they share a vertex, huh? Yeah. Looks good. Nice tree. Until, on a Friday, you discover something like this. What do we do now? Whoops. That isn't very tree-ish. Yeah? Yeah, that's right. That's right. So again, we have to patch up. It looked like a good definition until on a Friday we hit this. So the tree has as vertex set, or nodes, as we now sometimes say to distinguish it from the graph that we're decomposing, not because we've turned into computer scientists, but because it's good to have two levels. So the nodes of this tree are the blocks and the cut vertices. And now, what is the definition of edges formally? We now know the node set, the set of vertices, and we want these to be the edges. So, yeah, the obvious one being contained in. Right? Two blocks are always, if they, in the earlier attempt, formed an edge because they intersected, they now intersect in a cut vertex, as shown earlier. So two blocks, even by the old definition, will no longer be adjacent, never. They will only ever be adjacent to cut vertices. And the cut vertices will not be adjacent to each other in any intuitive sense, it's enough if they're adjacent to the blocks. And which blocks? Well, those that contain them. So here's the definition. Vertex set is all the blocks and all the cut vertices. Edges containment. It's a bipartite graph. One class are the blocks, vertex class are the blocks. The other vertex class are the cut vertices of G. And we form edges in this bipartite graph between any block and any cut vertex that it contains. And then one can go home and prove that this is really a tree. Right? It's still a lengthy sort of thing. We need to prove that there are no cycles. Okay, same proof as earlier. We then get a union of blocks that is still violates the maximality of its ingredients and so on. Yeah? So it's still a lengthy kind of thing, but it's easy. You just do it. Okay, so this is called the block cut vertex graph. Questions? No. Okay, so now we move on to something more serious. Let's see how we can construct not just the two connected graphs, but the three connected graphs. Let's start from the top. For a two-connected graph, we proved that we can find a path which we can delete and remain two-connected. Then we find another path which we can delete, whose interior we can delete and remain two-connected, and so on. We can dismantle it in a way that gets us down to a cycle. And at every step on the way, are we still two-connected? And the same can be done for trees. So, Lemma, it's 3, 2, 4, I think. If G okay, for every three connected G, that isn't a K4, there exists an edge such that G with that edge contracted is still three connected. So that means if we start with any three connected graph, we can contract edges, 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 one after the other. We can always find one to contract, so that at the end of the day we'll end up with K4. All right? Very nice. And that has a very nice proof, and the proof has an even nicer proof strategy. Here's the proof strategy. Ready? Play and see what happens. Okay? So, we have our big graph G, three connected. No. Let's not draw it. So we have the three connected graph G, and we want to find an edge that we can contract and remain three connected. So here's an edge, little e. Can we use that? Well, suppose not. And if we can, fine. If not, then let's call it xy. Then after contracting E, the new vertex, the contracted vertex VE, lies in a 2 separator with some other vertex Z, because after contracting this edge, we're no longer 3 connected. But then, as one can easily check, the 3 vertices x, y, z separate G, which is fine. G is 3 connected. But it's at least something we can observe. Okay. Now there are at least 2 components, and each of the vertices in the separator send an edge to every component. Because, say, if this vertex Z didn't send an edge to this component here, component of what? Of G minus x, y, z. If it didn't send an edge there, then the vertices in this component would be separated from the other components by only x and y. But then G wouldn't be 3 connected. So that exists for every vertex here. Okay. So now we follow our proof strategy, and we play. We say, oh, okay, we've got another edge to try. So, Z, V, and if that contracting this doesn't leave us 3 connected, then we have the same picture. Okay. Every vertex sends an edge to every component. Now let's look. We don't just want to start again, right? That would be stupid. We want to use what we have. So we can ask, where are x and y in this picture? Well, we can't have x and y in different components because they're adjacent. So let's say they're not in this, neither of them is in this component. So x is maybe here and y2, or y might be this, or x might be that. Then they're not z and v, right? X and y are not z and v. But one of them might be this, w. But my point is that we can find a component, let's call that D, that contains neither x nor y. Okay. Then let's look where this vertex lies in this picture. Okay. Now, we can get to this vertex from V directly by an edge. And so we can get to everything in D from V without hitting x or y or z. But that's a heureka moment. Talking about the ancient Greeks. We can get to everything in D from V without hitting x or y or z. So where does D lie in the left picture? Something we can get to from V without hitting x or y or z. It must lie inside this component, C. Can you see something? Can you smell something? We started with an arbitrary setting, then looked at an arbitrary component. But now we have found a setting where we can do the same, but with a smaller component. But nothing stops us from repeating that argument with that component. So we get smaller and smaller and smaller components, and that can't go on forever. Right? So we just say contradiction as long as we've got the setup right. And the setup at the start should now say, let's choose x and y and z so that C, one component of G minus x by z, is smallest. And then we can say contradiction here because we found 3 possible choices for x, y, z. They're called z, v, w, such that some component is in fact smaller than C. So we just mindlessly played around. Then suddenly we if we were alert enough, we noticed that there's a development in a direction which just goes on and on and on and on. And then we say, no, that can't happen. And then we just had to find the right setup to nail down the contradiction. That's it. Pretty proof, eh? That's Thomassen. Who proved that long after it was known in principle, long after the lemma was known. And the lemma is, in fact, one direction of what is sometimes called the Wheel-Theorem of Tutte. And that says that the 3 connected graphs are precisely the graphs that for which there exists a sequence of graphs where the last one is G and the first one is K4, such that each graph in the sequence is obtained from the one after it by contracting an edge. These are all 3 connected. So we just proved that if we start with a 3-connected graph, we can find such a sequence where we contract one edge at a time and remain 3-connected, and then we can only end with K4. By the way, where did we use in this lemma that G isn't K4? As one of those. We used it when we said, well, suppose we can't contract our arbitrary edge E. Why can't we contract it? Because after contracting it, we're no longer 3-connected. And then I said, oh, well, if we're no longer 3-connected, we have a 2-separator. That's not true. We have a 2-separator, or we're too small. Being too small is also a reason for not being 3-connected. And if we're K4 and we contract an edge, we're K3. K3 is not 3-connected, even though it doesn't have a 2-separator. So that's where we used it. Okay. So we've shown that when we have a 3-connected graph, we can contract edges one at a time to arrive at K4. Conversely, one can take any such sequence starting from K4 such that GI is obtained from the next one, GI plus 1, by contracting an edge. by undoing the contraction. So when we have GI, so this is GI, how do we, what GI plus 1s are allowed? Answer, almost any. They're all going to be 3 connected. So we now want this to be VE, a contracted vertex in GI plus 1. So this could perhaps look like this, right? Now, this would be the edge E, but if it did look like that, then GI plus 1 would not be 3 connected. It would have a vertex of degree 2. And the assertion now is that as long as we make sure that when we're expanding a vertex to form an edge, such that contracting that edge in the graph that arises gives us this graph, as long as we make sure that this graph has min degree at least 3, then that is again going to be 3 connected, and we can build any such sequence. So how could we expand this vertex to an edge? Well, for example, we could do this. Right. Just make sure no vertex, none of these 2 ends of E has degree only 2. So if this vertex has higher degree than 3, then it's even easier. So we could expand it like this. But even there, nothing stops us from doing that. Right? All these things are allowed. They will always produce a 3-connected graph when you expand in this way, as long as you make sure that your vertex degrees remain at least 3, which is obviously necessary for being 3 connected. Okay, so that's Tutte's Wheel-Theorem. Wheels are graphs like that. You have a cycle plus 1 additional vertex adjacent to everything. So K4 is the smallest wheel. And why is it called a wheel theorem rather than a K4 theorem? Well, you can, I think I wrote something about that in the notes. Has to do with Tutte's background in matroids and so on. Okay? So, questions about that? Yeah. Good. Now, let's ask, can we do the same with deletion rather than contraction? Well, when we have a 3-connected graph, can we delete until, as long as we're still 3 connected? And then what are the minimal graphs? Minimal 3-connected graphs that we get to. For contraction, there was only 1 minimal graph, 3 connected, K4. If you have a 3-connected graph that's anything other than K4, you can get smaller, you can contract. If you have a 3-connected graph where you can't delete a vertex or an edge without ceasing to be 3-connected, you can be pretty much anything. So there are too many minimal 3-connected graphs with respect to deletion, but if we change deletion to just a tiny little bit, rather than deleting an edge, we delete the edge and then suppress the end vertices of the deleted edge if they have degree 2 in the graph that arises in G minus E. Right, remember that? So if this is E, right, and that is G, then G minus E with a little dot on the minus would be you delete E, and then with that graph, and then both ends of E now have degree 2, so we have to suppress them, and then we get this, and that's a multigraph with 2 edges and 2 vertices. So this operation is defined for multigraphs, just to be safe. I mean, there might be other things here. And it might also be that only one vertex has degree 2 after deleting E, so the other might not. Then we only suppress that vertex. Right, so that's this operation. And the assertion is that another theorem also taught, and that says that, or is it a lemma? Yeah. Oh, no, I need another lemma first, but then after that it is a lemma. Okay. Oops. Let's do the other lemma first. 3, 2, 1. If G minus with a dot E is 3 connected, and G is a graph, rather than any multigraph, then G was already 3 connected. Right? It's sort of the way up, as we had it with contraction as well. If the smaller graph is 3 connected, then undoing the deletion keeps us 3 connected. And here we have to assume that after undoing this, we don't have parallel edges. Right, you can take a 3 connected graph, then just add a parallel edge, call it E. Then your 3 connected graph is that plus this edge minus dot that edge. Right? But that bigger graph isn't 3 connected. It's a multigraph that has a pair of parallel edges. So we must assume that the bigger graph doesn't have parallel edges. But as long as that's ensured, it will again be 3 connected. And the proof is horrible. So please find a nice proof. Maybe don't read the horrible proof in the book, so as not to spoil your intuition. Please come up with a nice proof. It's terrible. And even if you can't come up with a nice proof, don't read it anyway. It's sort of not worth it. I'm not going to ask it in the exams. It's a horrible little lemma. Right? But we need it. Okay, so, and then lemma 3 to 2 is the other direction. And that is for every 3 connected graph G, there exists an edge such that G minus dot E is again 3 connected, well, as long as G isn't K4. Okay. Right, now I'll just do it here, I think. And I tried to find a proof similar to this proof here, and I very seriously applied this ingenious proof strategy of playing, and I didn't play anywhere, so I didn't get it. So if you find a playing around proof, that would also be welcome, but the proof that does exist is very pretty. So let me give you that. We don't try to delete dot this edge, and if it doesn't work, we'll try another. Maybe one we gleaned from the failure of this one to keep us reconnected and so on. But we try to approach this G minus E with a dot from below. Notice that if we call this H, then G contains a topological H, namely which? Well, just G minus E without the dot. G minus E is a subgraph of G, and then we maybe suppress some vertices, but if we don't suppress them, the H that we get to by suppressing them has a subdivision before suppressing, that is this subgraph. So the idea now is to hunt for a TH, or let me call it a TJ inside G, and make this TJ as big as possible. And if we can't make it any bigger, then let's just hope and pray that we're only one edge away from G. Right? If we found this edge E, then G minus E is such a TJ. So, okay, this TJ, we'll call that H. So, choose H in G so that H is a TJ with J should not be the entire G, 3 connected. And choose it so that it has the largest number of edges. Okay? So, J is going to be 3 connected, like this K4, and G is going to contain a TJ, and we do that so that this TJ has as many edges as possible, and then we'll prove that J is going to be G minus E for some edge E of G. So why does such an H exist at all? Well, we can find a subdivision of K4 in any 3 connected graph. That's not so hard, right? So we can find a cycle because it's 2 connected in particular. Then let's call that C. Then we can find a C path P. And then we can say, okay, well, these 2 vertices don't separate those 2, so we can find a K4, something like that. I mean, there are some cases, so maybe This is just a single edge, but then there's no path from here to there, and so on. So it's easy. Every three-connected graph contains a subdivision of K4. So if we take this subdivision of K4, we'll have some candidate for H. So an edge with as many edges as possible certainly exists. And J isn't, K4 isn't D. Right, that's important here. Okay. Right, so okay. Let P, so H isn't the entire graph G. Why not? If H is a proper subdivision of J, then it has vertices of degree 2. G doesn't. So if it's not a proper subdivision, then it's equal to J, but then it isn't G either. So H is not G. H is not G. Let P be an H path in G. So that certainly exists. It might be a single edge, not as earlier. Chosen, if possible, so that the following holds. The end vertices of that path, UV, do not lie on the same possibly subdivided edge of J. Right, so we have our H here, and then we have this P, and we want to choose P in such a way that U and V, the ends, are not on the same subdivided edge. So this is the edge of J, this yellow edge, which in H was subdivided in this way. So this should be the same thing, right? Okay. That's just something we can ask. Why do we ask it? That came out right at the end of the proof. It's like your epsilon proofs in analysis. You find which epsilon you are, or which delta you ask for, which epsilon you need, right at the end of the proof. Okay, so don't worry about it. You'll see later why this came to be chosen. So let's see what happens if we can't choose P in this way. And of course, this is how, I mean, this used to be just cases. And asking for this choice of P, if possible, is just a way of sort of summarizing these cases in the shortest possible way. It's not the simplest possible way. It would be simpler to just do the cases one by one. But anyway, so this is how I wrote it up. So if P cannot be chosen with star, well, we still have a P. Then we can make some observations. One is that H and J are the same. H is, in fact, not a proper subdivision of J. Why? Because if H was a proper subdivision, like here, we could find a path. We pick any subdividing vertex and find a path in G from that subdividing vertex to the rest of J, or to the rest of H, avoiding the two ends of this subdivided edge. So once more, I'm trying to show that H is not a proper subdivision of J, that H equals J. Suppose not. Then we obtained H from J by subdividing some edges of J. Let's look at such a subdividing vertex. Then the two ends of the edge of J that we subdivided do not separate this vertex from the rest of J in G, because G is 3 connected. So we can get from this vertex, avoiding those two, maybe we'll hit here a few more times, but it doesn't matter. We'll avoid those two and then get to here. And this last little bit, from our last visit to the subdivided edge to here, that is a choice of P that does satisfy star. All right? If P cannot be chosen with star, then H is not a proper subdivision of J, and UV is an edge of J. Well, that's easy, because if UV wasn't an edge of J, then UV would be a path whose an H path whose ends do not lie on the same subdivided edge of J, if UV isn't. All right? J and H are the same, so UV must already be an edge of J. Okay. But now we get a contradiction, because P cannot also be just an edge. And that is because G doesn't have double edges. UV is already an edge of G. Then P, which is a J path, well, also it wouldn't be an H path. Well, in multigraphs it would be, but we're not in multigraphs. So G doesn't have parallel edges. So G has an internal vertex. P has an internal vertex. But then we could replace this edge UV with P to get a different H with more edges for the same J, or for an isomorphic J. Right? So replace UV with P to get an H with more edges. That is still a TJ with J not being G because it's the same as the earlier J 3 connected. Okay. So we get a contradiction. Hence, P does satisfy star. But now we're only one step away from the proof. We have U, we have P, path from U to V. It might be a single edge. We're no longer in the proof that star holds. So all this stuff was valid under the assumption that P cannot be chosen with star. Now we got to a contradiction there. Now we know that P does satisfy star, but we're back to square one with how P looks. So all we know is that P is an H path with n vertices at U and V. It might be a single edge, it might be longer. And so we also know that U and V do not lie on the same subdivided edge of J. So this again is the yellow edge is the edge of J, and it was subdivided when we formed H. And one of these subdivision vertices is now U. Right? I'm not saying that U must be a subdivision vertex. It might be that U and V are both vertices of J. Okay. So now we can just add P to H. U and V are not going to be an edge of J now, because then they would be on the same subdivided edge of J. They're not going to be an edge of J, so if we add this P, then we get an H prime that has an additional subdivided edge. And then we can look at the corresponding H prime. So J prime. So J prime is what we get from H prime by suppressing the vertices of degree 2. Then we basically get J back. But we get an additional edge, UV. Okay, but this H prime has more edges than H, and J prime is still 3 connected. So do we have a contradiction? We can't have a contradiction because then mathematics is not consistent. Something must be wrong. What is wrong? Well, H was chosen with J not equal to G. And it should be 3 connected, but J prime is 3 connected. H prime has more edges. So everything is better. So the only thing that can be wrong is that J prime is in fact G. Ha, bingo. And therefore, J is G minus this E, where E is UV. You have to be very careful when you check that proof. As, yeah, I think it's a nice proof. It has substance, has ideas, and of course you get to this only after doing that. But the idea is to grow from below, to start with something that is obviously a candidate, a K4, subdivision of K4. We're looking for subdivision of three connected graphs, want to make them as big as possible. Because we know that the graph we're hunting for, this, is a subdivision of something smaller, right? And we want it to be three connected. So this is three connected, and then without the dot, we get a subdivision of something three connected, namely of this, if the theorem is true. And then, if it is true, we may as well hunt for that directly. We will find something three connected, call it J, such that some subdivision of it uses as many edges of G as possible. And then we find that subdivision uses all the edges except one. That's E. Okay, so there's a similar converse as well. So this is also a theorem of Tutte, which is a graph of three connected if and only if we can find a sequence, G0, G1, G2, and so on, all the way up to G, which we call Gn perhaps, such that each later one gives rise to the previous one by deleting an edge with suppression. Exactly the same thing as before. And for the way up, we need this infamous lemma up there. That whenever we have something that is already three connected, and then we're creating something bigger in this way, then we remain three connected. And this time it's not trivial. Yeah, so that's it. Questions? No. Okay, we'll continue with one of the, perhaps the most applied and useful theorem of all of graph theory, Menger's theorem, next time, about connectivity. Maybe the marriage theorem is equally often applied, but Menger's theorem is certainly more substantial, and it's a lovely theorem. Also has an infinite version. All that next time. Okay, thank you very much.